everyone. So we have come across various measures of curvatures of surfaces. So in this video we'll try to see two new measures of curvatures of surfaces, namely the Gaussian curvature and the mean curvature. So to define these two curvatures, one must know an important mapping, namely the Weingarten map. So how do we define this Weingarten map is by using another important mapping called the Gauss map. So just orally I'll brief you out about the Gauss map. So this Gauss map is a mapping from the surface to the unit sphere, where each point of the oriented surface will be mapped to its unit normal of the surface at the point P, which will be in S square, that is unit sphere. So each point will be mapped to its unit normal, which is in the S square. So but then the rate at which this normal varies across the surface will be given by the derivative of this Gauss map. So by using this derivative of the Gauss map, we define the Weingarten map. That is, the negative of the derivative of the Gauss map is the Weingarten map. So I repeat again, the Weingarten map is nothing but the negative derivative of the Gauss map. So by using this Weingarten mapping, we'll define what is the Gaussian curvature as well as what is the mean curvature. So let's try to see the definition. Yes. So if you try to look at the definition of the Gaussian and mean curvature, so firstly, as I said, let W be the Weingarten map of the oriented surface S. So we are taking at the point P belongs to the surface. So the Gaussian curvature, which is been denoted by capital K, and the mean curvature denoted by capital H of the surface at S at the point P. So these are defined by, so let's write, so the K, that is the Gaussian curvature, is being defined as a determinant of the Weingarten map. And then what is the second one? The mean curvature is being defined as a half of the trace of the Weingarten map. So we have been already known what was the trace. Trace is nothing but the sum of the diagonal entries. So this is the definition of the Gaussian and the mean curvature. The determinant and the trace of the linear transformation is nothing but actually the determinant and the trace of the matrix that corresponds to the linear transformation. So by using any of the bases, that means with respect to any of the bases, for a given linear transformation, we can find the matrix. So for that particular matrix, in this case, in fact, we can call it as a Weingarten matrix. So for that, we will find out the determinants and the trace, which will give us the definition of this Gaussian and the mean curvature. So wherever the map we have used, there we are going to replace it by the matrix. And of course, it could be with respect to any of the bases. So here, these determinant and traces will depend only on the linear transformation, and it is independent of any of the bases that we choose. So by using these definitions, let's try to see some of the observations by using our previous knowledge. Yes, let's see the observations. So the first observation what we need to observe is, if you consider the matrix corresponding to the Weingarten map, we have already seen that this matrix do have the eigenvalues. The matrix corresponding to the Weingarten matrix has the eigenvalues, and in fact we know that they are nothing but our principal curvatures K1 and K2. This we have already seen. So now the moment when we have the eigenvalues for a given matrix, how do we find its determinant? Why do we require its determinant is, just now we have defined that the Gauss curvature is being given by the determinant of the matrix corresponding to the Weingarten map. But then the moment when the Weingarten matrix, of course the matrix corresponding to the Weingarten map have the eigenvalues K1 and K2. So for this particular matrix having these eigenvalues, the determinant will be given by the product of the eigenvalues. Here it is a product of K1 and K2. And then what else we require? If you look at the trace of such a matrix, what do you mean by a trace? Trace is nothing but the sum of the diagonal elements. Here our diagonal elements are nothing but our eigenvalues. So if you look at the trace of the matrix corresponding to the Weingarten map, this is nothing but the sum of the diagonal entries. That is nothing but K1 plus K2, because our principal curvatures are the diagonal elements in this case. But then we have defined our mean curvature to be half of the trace of the matrix, and therefore it will become half of the sum of the diagonal entries. So this will be the mean curvature in terms of our principal curvatures. But then the second observation what we need to observe is, if you look at our Gaussian curvature, it could be all three possibilities. The values of Gaussian curvature can be three possibilities. One can be Gaussian curvature can be greater than 0, Gaussian curvature can be less than 0, and Gaussian curvature can be equal to 0. So let's see when it can happen. Say for example, if you look at the Gaussian curvature is greater than 0. What do we mean by this? Just now we have observed the Gaussian curvature is nothing but the product of the principal curvatures. So I can have the Gaussian curvature greater than 0 provided if my both k1 and k2 are greater than 0 or both k1 and k2 less than 0. In these two cases we will get the Gaussian curvature to be greater than 0. But then we must know what to exactly mean by having a principal curvature greater than 0 or a principal curvature less than 0. So let's try to interpret geometrically. Say for example, if you try to look at a surface of this type and consider this point, particular point, and then try to observe the normal here. Suppose if this is your normal and this is your considered point, here it is like ball up towards out towards the normal. It is like ball out towards the normal. Could you see that? So wherever you have this curve, it is like up towards the normal. Here in this case you will have your principal curvature to be less than 0. Closely observe this. I am writing it as a small k, which means it is the principal curvature. So whenever we have of this particular positions, in this point you have the principal curvature less than 0. What do you mean by principal curvature greater than 0? The same way you can consider and observe at this particular point where the normal is of this shape, and here if you observe it is like ball down towards the normal. Could you see that? So in this particular point where you have the ball down towards the normal, you will have your principal curvature. Again I am writing small k, which is greater than 0. So this is principal curvature. So this is what we mean by having, because here we have the principal curvature less than 0. So when both the principal curvature are less than 0, you will get the Gaussian curvature to be greater than 0. So similarly, if you have both the principal curvatures greater than 0, you will have the Gaussian curvature to be greater than 0. So now if you coming to the second case, what do you mean by k less than 0? So now we know that when it can happen, provided one among them can be negative, isn't it? So that means what? My k1 can be less than 0 and k2 can be greater than 0. In that case the product will be negative. Or my k1 can be greater than 0 or k2 can be less than 0. When it can happen, do we have a surface and can we see a point on the surface where we can get the Gaussian curvature to be less than 0? Yes. Try to observe this figure. If you try to observe this, so let us consider a point here and draw the normal, in fact unit normal. So if you closely observe here, it is like the ball up towards the normal here, and the other one is ball down towards the normal. Here it is up towards, here it is down towards. Wherever it is up towards, we know that our principal curvature, small k, it is less than 0, and wherever it is down towards, it is small k greater than 0. Now at this point you have one curvature up towards the normal, so principal curvature is less than 0. Another is one down towards the normal, so principal curvature is greater than 0. If you take the Gaussian curvature, it is a product. So let me write it as k1 and k2. Of course it can be the other way too. So the product of them will be negative. So at this point we have the Gaussian curvature to be negative. So whereas in this case both the ones are up towards the normal, so you have the Gaussian curvature greater than 0 because both you get less than 0. The product will be positive, of course. And this is 1. And when can it be equal to 0? There are two possibilities. One can, at least one among them can be equal. That is k1 equal to 0 and k2 is not equal to 0. And that means k2 can be positive or k2 can be negative. That means one can have the ball up towards the normal or down towards the normal. Whereas other way is both can be 0. What do we call when we have a point where both the principal curvatures are 0? They are nothing but our planar points. That means what? If you consider any plane, if you consider any point here, the principal curvatures are 0, and thereby that means when you observe at that point the Gaussian curvature is 0. And then there is one more thing that we can discuss. Of course in these particular surfaces and these particular points we have seen the Gaussian curvature. Do we have a surface where we can observe all these three types of Gaussian curvatures? Yes, we can observe the important one, which is the torus. Say for example, let's try to draw the torus. Yes, suppose if you assume this is your torus, and then yes, just assume this is your torus, and then let the mid part is this. So if you closely observe, take a point
outside the surface. Say for example, if I am taking a point here and then I am just trying to draw my unit normal, this is my unit normal. If you try to observe here, both the one is down towards the normal, isn't it, and the other one is also down towards the normal. You just try to visualize in 3D, both this as well as this, both of them are down towards the normal. Whenever both of them are down towards the normal, your k1 will be greater than 0, k2 will be greater than 0. Just now I was saying you that whenever it is down towards the normal, your principal curvature will be greater than 0. So when both of them are greater than 0, you will have your Gaussian curvature capital K to be greater than 0. Suppose if you consider a point inside, say for example I am talking about the inner part. If you consider a point here, say the normal is of this shape, and if you observe, it is like one is up towards the normal and the other one is down towards the normal. You need to visualize in 3D. So the one part is like this, another part is like this. So in this case, when it is up towards the normal, your principal curvature is less than 0, and when it is down towards the normal, your principal curvature is greater than 0. And in this particular point, if you observe, your Gaussian curvature is less than 0, because when you take the product of them, it will be negative. And do we have the points where both the curvatures are 0? Of course we have. If you take any point in this middle part, middle curve, exactly the kind of axis for this torus, if you consider the part exactly here, one can easily observe that the both principal curvatures will be equal to 0, and thereby you get the Gaussian curvature.
So we have found that the definition of the Gaussian curvature is nothing but the determinant of Weingarten matrix. So but then till now we don't know how one can get the Weingarten matrix, because Weingarten map was been given. Then for a given surface patch on this oriented surface S, how one can find the Weingarten matrix. So we will prove one of the important result which will enable us to find out the Weingarten matrix. So by using which one can easily talk about the Gaussian and the mean curvatures, because the moment when we get the Weingarten matrix, we are done with that. The determinant of that matrix will give us the Gaussian curvature, and half of the trace of the matrix will give us the mean curvature.
So if you look at this proposition, so let sigma be the surface patch of an oriented surface S. So then the matrix that is corresponding to this Weingarten map at the point P with respect to this oriented surface S, and of course we from here onwards will call this as a Weingarten matrix. So with respect to the basis sigma u1 sigma v, so of this particular transformation, we will be that matrix will be given, the Weingarten matrix will be given by f inverse 1, that is f1 inverse times f2. So here we will try to prove this result. So we have already seen that the mapping, the Weingarten map of the sigma u will give us the negative nu, that is negative times nu, and the Weingarten map of sigma v will give you negative times nv. These things we have already found out. So now if you look at this nu, this is in the tangent plane. So any vector in the tangent plane could be written as a linear combination of these elements. So let's try to write it as a times sigma u plus b times sigma v, and similarly minus nv also could be written as c times sigma u plus d times sigma v. So here we are trying to prove that by using these elements, that is a, b, c, d, which we got as a scalars when we tried expressing these two in terms of the sigma u1 sigma v, this will enable us to find out the Weingarten matrix. In fact, so we will show that this Weingarten matrix will be given by the 2 cross 2 matrix of a, c, b, d. So we are trying to prove these results. So these scalars we got by expressing these two as in the linear combination of these two elements. So now, so by using this linear combinations, we will try to define. So we have already know, just now we have got these things. So what we are trying to do it now is, we are trying to take the dot product of this with respect to sigma u1 sigma v, that is the dot product of these equations, these two equations which we got just now, with sigma u1 sigma v. So I'll just try to make out one. So suppose if I take the dot product of negative u times sigma u, just now we have seen the negative nu is nothing but a sigma u plus b sigma v, this dot sigma u. So when we try to expand this, we get a times sigma u dot sigma u plus b times sigma v dot sigma u. So if you try to recall, the sigma u dot sigma u is nothing but norm of sigma u whole square, which is nothing but our E. So if you try to remember the first fundamental form, this is what the E we denoted for this, and sigma v times sigma u was of course our F. So now we tried expressing this, the dot product of this gave us AE plus BF. But then if you closely observe this, by our second fundamental form, so if you leave this excluding this negative sign, nu dot sigma u was nothing but minus L. So minus nu dot sigma u will be L. So we got L is equal to AE plus BF. So similarly, if you try to take the dot product of the negative nu with sigma u as well as the negative nv with these two, we will end up with these equations where we get m is equal to AF plus BG, and then another equation for m will get it as CE plus DF, and an equation for n we obtain as CF plus DG. So these are the various equations that we end up. So now these four equations which we got, we can try to express them in the matrix form. What is that? Let me write down here. So if you write down this as LMMN, this is nothing but EF FG times matrix AC BD. Closely observe, if you take the first element of this product matrix, you will get A times A plus F times B. What is that? That is nothing but this equation, A times E plus B times F. So the first row and the first column, these linear combinations is giving you the first element, that is nothing but our AE plus AF, BF. So you can closely observe all the other elements corresponds to these four equations. So we tried expressing these four equations in the matrix form. But then what do we know about these matrices? The 2 cross 2 matrix of LMMN, it is nothing but our F2. So this matrix LMMN, this is nothing but our F2, and what we got was EF FG. What was this? This was nothing but our F1, and what was been left out? That was AC BD. So let me write down that as AC BD. So this will enable us to find out the matrix, Weingarten matrix with respect to the basis sigma u and sigma v to be F1 inverse. Just we are bringing down some simple calculations which will give us AC BD. So this is how we proved that the Weingarten matrix with respect to the basis sigma u and sigma v. Again I specify, basis is not important here. With respect of any of the basis, we can find this particular matrix. So once if we get this matrix, the determinant of this matrix will give us the Gaussian curvature, and half of the trace of this matrix will give us the mean curvature.
So we have got the clear definitions of Gaussian curvature and mean curvature, because we could find out the Weingarten matrix whose determinants and trace could help us to find those curvatures. But in fact, we can find some formulae for these two curvatures by which we can directly compute for a given particular oriented surface at a point. So let's try to take out some of the formulae for these two, where by using the previous results it is very easy to prove the formulae, so that one can easily use off on that.
So these are the two formulas to find out the mean curvature and the Gaussian curvature. So let's try to prove that these two formulas. So we already defined that our Gaussian curvature is nothing but the determinant of Weingarten matrix. But then just now we proved the result that Weingarten matrix is nothing but F1 inverse times F2. So in fact now if you closely observe this, I can rewrite this as determinant of F1 inverse. I could send it to the denominator, thereby I get F2 by F1. So just observe this, this was our F2. So the determinant of this is nothing but Lm minus m square. So the determinant of F2 what we got was Ln. So let me just rewrite this, this was n. So Ln minus m square divided by the determinant of F1, because here we are using the property that is determinant of F2 by F1 is equal to determinant of F2 divided by determinant of F1. Remember here our determinant of F1 is clearly not equal to 0, because for a regular surface we have already showed that this will never become equal to 0. So therefore we can clearly define this is Ln minus m square divided by, and similarly the way we define this determinant of F1 will be Eg minus f square. So by this
we have proved that the Gaussian curvature is nothing but ln minus m square divided by Eg minus f square. So to compute H, so what we need is the trace of the matrix. So if you closely observe the Weingarten matrix, it was our f1 inverse times f2. So how do we find the f1 inverse? So what was our f1 was the 2 cross 2 matrix EF FG was our f1. So f1 inverse, it will be 1 by determinant of f1 times the adjoint of f1. So what was the adjoint of f1? Just interchange the diagonal elements, so by which we get G, E, and change the signs of the anti-diagonal elements. It will be negative f1, negative f. So this is our f1 inverse multiplied with our f2 was clear. It was 2 cross 2 matrix of LM, M, N. So this is nothing but 1 by, what was determinant of f1? Just now we have written determinant of f1 was Eg minus f square. So times G minus f E times L M M N. So if you try to simplify this whole matrix, so the first term let us keep us the same and we will try to simplify this matrix. So if you try to simplify, we will get a 2 cross 2 matrix of, so this will be GL, in fact I can write it as LG minus MF. For time being I am just writing directly, it is MG minus NF, and this will, if you simplify, you will get ME minus LF, and if you try to simplify the second row and the second column, you will get NE minus MF. So here our matrix got simplified because we will just introduce this element inside. So this, the denominator part will be there for every element, and then you can say that the trace of the matrix is this sum of the diagonals. So directly let me write the trace of f1 inverse times f2 is nothing but the sum of the diagonal elements, where we will get Lg minus 2mf plus Ne divided by, this is common for all the elements, Eg minus f square. We got only the trace, but remember our mean curvature was a half of the trace. So what will be that? If you take the mean curvature H, this is half of trace of this f1 inverse f into f2, which is nothing but, I am going to write that half in the denominator, Lg minus 2mf plus Ne divided by 2 times Eg minus f square. So this is our mean curvature which we have proved. So we can just check, this is what we wanted to prove here. So we have just proved the mean curvature as well.
1, 2, 3, 4, 5, 6, 7, 8.